In this video, we will delve more deeply into how to estimate a population proportion with a confidence interval. By the end of the lesson, you should be able to state and check the conditions necessary for constructing a confidence interval for a population proportion. You should be able to determine the critical value for calculating a C% confidence interval for a population proportion using a table or technology, and you should be able to construct and interpret a confidence interval for a population proportion. So let's remember that for any confidence interval, you have a point estimate, and then you add and subtract the margin of error on either side of that in order to create a confidence interval. More specifically, because the margin of error is comprised of the critical value times the standard deviation of the statistic, we can say that a confidence interval is a point estimate plus or minus a critical value times the standard deviation of the statistic. Remember that the point estimate for a population proportion is just p hat, and the standard deviation is computed by taking the square root of p times 1 minus p over n. The issue we have when we're trying to construct a confidence interval is we're trying to estimate p, so we don't actually know what p is. And therefore, we use what's called the standard error of the statistic as an estimate for the standard deviation. When the standard deviation of a statistic is estimated from data, the result is called the standard error of the statistic. By substituting the standard error for the standard deviation, the general formula looks pretty much the same. The only thing that's different is, instead of p, we use p hat. The symbol for the standard error of p is either SE sub p hat or S sub p hat, and it depends what book you're looking at. Standard error is interpreted pretty much the same way that you would interpret standard deviation. We say that with repeated samples of size whatever, the sample proportion of whatever it is we're looking for typically varies by about whatever the standard error of p hat is from the true population proportion. All right, so let's try it. Katy Perry is one of the most popular accounts on Twitter, with more than 100 million followers. Mr. Starnes wonders what proportion of Katy Perry's Twitter followers are female. So he selects a random sample of 500 of Katy Perry's followers. In the sample, 308 are female. Our task is to calculate and interpret the standard error of p hat for these data. So what I'm going to do is use p hat in place of p in the formula. So I've got 308 out of 500 times 1 minus that value, all over our sample size, which was 500. Take the square root of that, and the standard error of p hat is 0.0218. That's the calculation. Now the interpretation. In repeated samples of size 500, the sample proportion of Katy Perry's Twitter followers who are female typically varies by about 0.0218 from the true population proportion. So now we're going to talk about the one sample z interval for a population proportion. It's also known as a one proportion z interval. When the conditions are met, and we'll talk about the conditions in a moment, the C% confidence interval for an unknown proportion is p hat plus or minus z star, that's your critical value, times the square root of p hat times 1 minus p hat over n. Z star depends entirely upon what percent confidence you would like. It's the value that has the area between negative z star and positive z star that's equivalent to C%. The specific formula for a one sample z interval for a population proportion is not on the formula sheet that you will have for the exam. However, the formula sheet does include the general formula for a confidence interval and the formula for the standard error for the statistic p hat. So everything you need is there, you just have to put it together. All right, so conditions for constructing a confidence interval about a proportion. First of all, random. The data have to come from a random sample of the population of interest. Otherwise, if your data is no good, you can't really create a meaningful confidence interval. 10%, when sampling without replacement, make sure that n is less than 10% of the population. And when you're dealing with an experiment, instead of the random selection, we need random assignment to treatments rather than a random sample. And the 10% condition is no longer necessary. Large counts, both NP and n times 1 minus p, have to be greater than or equal to 10. Those should both be p hats. All right, so here's an example to check the conditions. Let's verify the conditions are met for that Katy Perry example. Here's what the problem stated. All right, randomness. Well, yes, it says that Mr. Starnes selected a random sample. 10%. Yes, 500 is definitely less than 10% of 100 million. Large counts, yes. N times p hat is 308. That's greater than or equal to 10. And n times 1 minus p hat is 192, also greater than or equal to 10. You'll notice that the n times p hat is 308. That's actually the sample, like the proportion in the sample, the 308 females. And then 192 is the rest of them. All right, what happens if the conditions are violated? Well, without the randomness, you've got bad data. You can't do anything with it. The 10% rule will give us a value that's too large if it's violated. So if we made a C% confidence interval, our capture rate would actually be higher than C%. As far as large counts are concerned, if we made a C% confidence interval from data where the large counts was violated, the capture rate would almost always be less than C%. So your claim would be inaccurate. All right, so how do we calculate the critical value? In other words, how do you figure out what Z star to use? Well, there's a table that you can use that is in your book. It's also provided to you for the exam, and you can also use your calculator. The table is much easier, so I encourage you to take a look at it. This is a picture of what you'll get on the exam if you take it in person, and I assume if you take it online as well. They call it Table B. You can see where it says Table B, T distribution critical values, and you'll also see T up at the top. Don't worry about that. Look down at the bottom where I've highlighted it in yellow, and it says confidence level C and a bunch of percentages. I'm going to just expand that so we can look at it more closely. So look at those numbers, 50%, 60%, 70%. Notice the 95%. That's a very popular confidence interval level, and there's a 99% also popular. The numbers directly above the percent you're interested in are the ones you want. So as long as the C% you want is on this table, the Z star is found directly above it in the infinity row of the table. So if I want a 95% confidence interval, I'm going to use 1.96 as my Z star. If I want a 99% confidence interval, I'll use 2.576. So if I wanted a 98% confidence interval, what value would I use for my Z star? Think about that for just a moment. Well, I hope you picked 2.326 because that's the number directly above the 98%. All right, if you don't have the table handy or you don't want to use it, you can use your calculator. Remember, Z star is the critical value for the standard normal curve with C% of its area between minus Z star and plus Z star. That picture shows you what it is you're looking for. Now, if you want those cutoffs, you're going to need to know your C%. Half of the difference between 1 and C is what's in each tail. So 100% of the data is under the curve. C% of it's been highlighted in yellow. If you subtract 1 minus C and take half of it, there's half in each tail. All right, so to find Z star, we use inverse norm. That's in the distributions menu in your calculator, in the same place you find normal CDF and binomial CDF, etc. We just need to know the area to the left of the critical value. So you can use the one up at the right, or you can use the one on the left, because once you get the value, you're going to add and subtract it. So you can either do 1 minus c over 2 or 1 plus c over 2 and do inverse norm for that value. C will be written as a decimal, obviously, because we're looking at a proportion under a curve, and proportions are always between 0 and 1 inclusive. All right, try it. Either your table or your calculator, find the critical value z star for each of the following confidence intervals. All right, well, for the 90%, I hope you found 1.645. For the 97%, I hope you got a z star of 2.170. And for the 99.5%, I hope you got a z star of 0.2807. All right, so let's put it all together. We need to state the parameter you want to estimate and the confidence level. You need to plan, which means identify the appropriate inference method and check conditions. You need to do the math if the conditions are met. And then you need to interpret your interval in the context of the problem. That's the conclusion. Previously, I've called this I can see, which stood for identify the interval by name or formula, and identify the parameter, check your conditions and assumptions, plug in the numbers, and then state your conclusion in context. You can remember this however you like. You can do state, plan, do, conclude, or you can remember I can, as long as you can remember what all those things mean. All right, we're going to pause, and I'm going to ask you to watch the next video in this series in a moment.